So good afternoon once again, and I will discuss today the countability, countable species, which are the topological spaces with specific properties. So, for example, the first definition is first countable species. So, like we have in set theory, we have a first countable set, second countable set, and so on. The same way, we have similar way we have countability axioms for topological spaces. So first kind of space is the first countable space. So that is a topological space X has a countable basis at a point X in capital X. So capital X is a topological space and small x is a point of capital X. Then we say that the topological space has a countable basis at X if there exists a collection which is countable Bx, which are the sets. So this is a countable set. So it can be written as the sets depending on natural numbers. So b1, b2, b and so on of open sets uh, containing. So each of this set contains the point x. So therefore it is called the basis at a point x, such that so it is kind of a locally compact space. So basically we are discussing this property at a particular point x. So what we will do is we will not consider the every open set, but we will consider a neighborhood of this point. So each neighborhood of the point x uh, basically intersects with one of this set. So that means it contains at least one point of x, one point of the element of bx. So basically it intersects with each bn. So that is basically x belongs to bx, uh, x belongs to bn, which is subset of u. Sorry, what I've written is that x contains at least one, not point, one element of bx. So one and element of bx is of this form for some particular n, for some n belongs to n. So this u is a uh, neighborhood of x. So in diagram, if we understand that, then x is a topological space, and I have a point x, and then I have b1, b2, bn around x. So all these are the open sets. So whenever I take a neighborhood which is an open set containing x, that will intersect one of these b1, b2, bn. So let us see one simple example that if we consider a matrix space, for example. So let x be a matrix space with respect to the matrix D. So X is a matrix space. That means on that we have a distance function defined on that, and with respect to this distance function, can I find a family of open set around X, so that whenever I take any open set around X which is U, then it will intersect at least one element from that collection. So let us consider a fixed family. So consider, let us say Bx. So this family I basically need which is concentrated at X kind of thing. So what I will consider is I will consider the balls which are centered at X and its radius is kind of decreasing. So I can take radius is 1 upon n for every natural number n. So so now you can see why we are denoting it by Bx, because basically it is kind of centered at X, and uh, this is a particular family which is the open sets around the point X and its radius is basically decreasing. So whenever we take any open set, so now let us start with let X belongs to U and U be any open set, right? So since U is any open subset of X, so what is happening is that we have a matrix space X and in which we have a point X. Now around X we have a for n equal to 1 we have a ball of radius 1 centered at X. So this is radius 1 ball. So that is a kind of unit radius ball centered at X. Then we can consider the radius half. So that will be this ball. Then we'll have a radius 1 by 3. So all these are the elements of Bx. So now what we will do is we will select any open set around X. So for example, I am considering this particular, let me use some other color maybe. So suppose we are taking this particular ball. So this is an open set which contains X, and then you can see that there is at least one natural number we can find so that this open set U will intersect with one of the ball. In fact, one of the ball will entirely contain in this open set U. So let us write down the argument that since X comma D be a matrix space, we can always find the at least one natural number n belongs to n, so that the ball centered at X and radius 1 by n is entirely contained in U. So this is basically element of this family B of X. So whatever X is given and U is given, if we can find a family so that at least one member of the family we can always find for each for each u around x. So that is this theorem. So in particular, even if we go in a special case, if we take x to be R with the usual matrix, then uh, and further, if we take x equal to 0, so then what will be b of x? B of x will be b of 0, and that will be nothing but ball center at 0 and radius 1 by n. So that are basically the intervals minus 1 by n to 1 by n for all natural numbers. So now the same proof will give us that if I take if we take any open set around 0, then uh, so open set, let us say u around 0, then u always contains at least one natural number such that uh, this will be contained in u. Right, so this is basically why it is happening, because of the Archimedean property, or in other words, you can say the sequence 1 upon n will converge. So basically, whatever small open set you take around 0, you can always find 1 upon n which is contained in u. So that is same as for every epsilon we can find a natural number such that 1 upon n is less than epsilon. Right, so this is basically the countable basis at a point x. And if we can find such a basis around every point, then such a space is called first countable space. So a topological space X having a countable basis at each of its point, then X is called first countable topological space. Right, so this is basically the first kind of space where at every point we can find a countable basis. So there is the similar way we can define the second countable space. So let us see the definition. The first countable space, we already seen the example that all the matrix spaces are basically first countable spaces. So let us see what is the definition of second countable. So a topological space X has a countable basis if there is a countable collection uh, countable collection B of subsets of X that is itself a basis for the topology on X. So we know that every topological space has a basis. Now question is whether that basis, that collection itself is a countable collection or it is uncountable collection. So if we have a topological space which is a basis, which that collection B itself is a countable collection, then the topological space X we will call a second countable space. So, so in this case, basically, we say that X is second countable. So second countable means it is second countable topological space. So what is the example? So example is very simple. So if we take, let x to be the set of real numbers with the standard topology. So so now if we consider a particular basis, which is, we know that the set of real numbers with the standard topology, the basis is open intervals, right? But now I need a countable basis, so that means I need to modify the basis. So what I will consider a basis which is the set of the collection A comma B, where A and B I will take only rational numbers, right? So question is that whether this is a basis for the standard topology or not. Certainly this is a countable set, right? This is a countable set. So if we can show that this is a basis for topology, first of all, it is a basis that we need to check, and second we need to check is that it generates the same topology, which is the standard topology. So basis is more or less clear, because if I take any point x, I can always find a interval which is which has the rational endpoints, and it covers that particular x, right? So that we can do by the rational density theorem we can use, or whatever, we can always find such a pair. And then once uh, we have, so if you want, we can check that also. So if x is a real number, then there exist A and B rational number such that x minus 1 less than A less than x, and x less than B less than x plus 1, because of the rational or irrational density, depending on x is rational or irrational. Actually we are using rational density because we are finding rational number, right? What is rational density theorem? That you take any two real number, there is always a rational number in between them if they are distinct. So x and x minus 1 are distinct real numbers, so there is always a rational number in between them. And a is less than b because a less than x less than b, right? So therefore what we get is x belongs to open interval ab, and ab are rational numbers. So this is first part, that this is a basis. Second part is also simple, that if I have a number x which is in a1 b1, and x is also in a2 b2, then there exists a3 b3, so that x belongs to a3 b3, which is contained in a1 B1 intersection A2 B2. Right. So here what is A3 B3? You just take minimum or maximum, right? So A3 is basically maximum of A1 A2, and B3 is minimum of B1 and B2. Right. So it is clear, because if I have two intervals A1 B1 and A2 B2 which contains X, then I can always find a interval which is contained in both of the interval, and it contains X. Right. So therefore B is a basis that we verified, and basis for X equal to R, and then it generates the standard topology. That is also clear, because uh, if you have any open interval with okay, so let B dash be the basis for the standard topology on X equal to R. Then B and B dash will generate the same topology. Why? Because if X is in C comma D, where C and D are real numbers, then I can always find X belongs to AB, which is contained in CD, where A and B are rational numbers. Right. So this is basically the hint to prove that these both bases will generate the same topology. Again, here also we will be using rational density theorem. So what we proved finally is that therefore the standard topology on R has a countable basis, has a countable basis. So since it has a countable basis, therefore it is a second countable topological space. Right. Because once it has a basis which has the topology having the countable basis, that space itself is called second countable. So now question is there whether what is the relation between first countable space and the second countable space. So that is a small result that so if X is second countable, then X is also first countable. So basically every second countable space is always a first countable space. So that we need to verify, and more or less it is clear from the definition itself, because the topological space itself is countable, then the collection at a particular point is also we can consider that is a countable. So let us see how to find that. So if I take B to be the collection of of let us say Bn, B1, B2. Bn is the basis for topology uh, be a countable basis for x. So how we get this? Because x is a second countable, so it has a countable basis. And once it has a countable basis, then for each x in x, the sub collection, let us say b of b at x. So bx, what we will consider is we will consider the open sets around the point x. So we will not take the entire collection B, we will collect only those sets, those elements of B. So let us write this as capital B belongs to B such that X belongs to B. Right. So we'll select only those basis elements which contains X. Right. So then now we can see that uh, then it is clear that Bx is countable because Bx is subset of B basically. So we are not taking all the elements of B, but we are taking only the elements of B which contains X. And since B itself is a basis, it satisfies that condition. So once again, Bx is a subset of B for each X in any open set U, where U is open. We know that there exists a basis element. Basis element, let us say B belongs to B such that X belongs to B contained in U. Right. But note that this B always is also element of B at X, because this B contains X, and then we know that every basis element which contains X is already in Bx. That is basically the definition of Bx. Right. So, so that is what we proved, that therefore Bx is a countable basis at the point X belongs to X. Right. And therefore X is first countable space. So this small lemma will prove that every topological space which is of second countable is also first countable set. So these are the two types of spaces. There are other types of spaces which is regular and normal spaces that will come back again. But before that we need this definition. So this is regarding dense subsets. So a subset A of a topological space X is called dense subset if its closure is X. Alright, and then we know what is the equivalent condition of the closure of a set, so that we can use and we can deduce this remark that A closure is X means that every non-empty open subset of X, open subset of X intersects A, right? So that is basically if any X belongs to A closure, then every neighborhood of X will intersect A. So that is same thing we have written here, that every non-empty open subset of element of capital X that intersects with A. So example is what? Example we already know from real analysis that if we consider the set of rational numbers, then it is dense in real numbers. So Q closure is R. And this will give us a uh, particular notion of a space that is called the separable space. So topological space X is called separable if there exists a countable dense subset. So this will give one example that since R has a countable dense subset, R is separable. Right. So first example is R is separable. So here R is separable means basically standard with respect to the standard topology. So now we want to show one theorem that every second countable space is always separable. Every second countable topological space X is always separable. So basically using the second countability criteria, we need to find the separable subspace, right? So we will uh, we will consider a basis since X is second countable space. Space we have a countable basis, right? So since X is a second countable space, X is a countable basis. So this countable basis we can write as uh, Bn n belongs to right. So in first countable space we have a countable basis around given point X, but here in the second countable space we have the basis arbitrary basis, so it is not necessarily around the point X, but the basis of the topology itself is countable collection. So this is that collection. Since X is second countable, it has a collection of basic open sets, and that particular collection itself is countable, right? So so now we need to construct a particular space which is dense. So we need to construct a set which is a dense subset. So what we will do is we will choose at least since we need a subset which is countable, and here we have a family which is countably many elements. So what we will do is choose at least one element of this each bn. Right, so choose xn belongs to bn for each natural number n. So then we'll get uh, we can denote this set, the set of all xn, as d, and the claim is that this is a particular this is actually a dense subset of x. So if you can show that this is dense in x, that means we have a countable collection, the countable subset of x which is dense, right? And once we have a countable subset which is dense, the space itself is a separable space. So now let us try to prove this. So now we need to prove D closure is x, and to show D closure is x, we need to check this property that every non-empty open subset of x intersects with A. So let us start with any neighborhood in x. So let U be an open subset of x containing a point y. Right. So U is an open subset of x, and y is any point inside U. So since U is open, uh, so let us call it x itself. So we have a topological space X in which we have a point X and a neighborhood U. Right. So for this particular neighborhood U, what we will do is that since U is open set, and since we have a basis element, since we have a topological basis, there must be a basis element which is containing X and inside U. Right. So since B is a basis, there exists a basis element so that X belongs to basis element which is contained in U. Right. So X belongs to Bn contained in U. So now what does this give? This gives us that therefore this uh, so this is, from this we get Bn is contained in U, right? So since Bn is contained in U, Xn belongs to Bn which is contained in U. And once Xn belongs to Bn which is contained in U, what we get is that therefore Xn belongs to, we know that what Xn belongs to D, right? Xn is element of D for some n, some particular n. So if you want, we can fix this basis element and call it n naught, so that will be better. So then this Xn naught, which is element of D, and it is element of Bn naught also, and which is contained in D intersection U. Right. So that will give us that D intersection U which contains this point Xn naught, therefore it is non-empty set. Right. So that will give us that every neighborhood U intersects D. every neighborhood or every open subset of X intersects D. So therefore D closure is X. Alright, so it is basically the generalization of the rationals are dense, because if you take any neighborhood of in the real line, that is every open set in the real line, that always intersect the rational numbers. So this is exactly the generalization of that particular result. Okay, so then I think this is enough for today lecture.